about these accretion disks.
Sorry, PowerPoint.
There we go. So a brief outline, I'm going to talk a little bit, just introduce what is a supermassive black hole, what is an active galactic nucleus, which is basically like a supermassive black hole that's growing, what is our standard picture of how these things grow, and how can we test this using echo mapping. So this is like a very nice movie poster style artist impression, part of a series drawn by NASA called Visions of the Future. So it's like an artist impression of a black hole and the space around it. So what is a black hole? There are a lot of astronomers in the audience, I think, so go get a beer. But if I throw a ball straight up into the sky, it's going to fall down. If I throw a ball straight up into the sky with about 7 miles a second speed, it's not going to fall down. Because that's higher than what we call the escape velocity for the planet Earth. If I put more mass into the same volume, so make the planet Earth heavier with the same size, the escape velocity goes up. I have to throw even faster to get that ball up and away. At some point, the escape velocity exceeds the speed of light, and then basically we get a black hole, because light can't escape. It's too slow. There you go. Black holes are real. They exist. We weren't very sure about this until 2017, but this is the first image of a black hole from what we call the Event Horizon Telescope project, which is like a massive, huge undertaking where they aimed a bunch of telescopes all around the world to get this first image of an actual supermassive black hole. And you can do this for black holes that are like a combination of very close and very big. So this one's kind of close. It's not in our galaxy, but it's very big. So you can get a picture of the, how do I do the laser thing? There. You can get a picture of like the very inner regions of this black hole. And so in astronomy, we kind of class black holes by weight class. The smallest ones we call primordial black holes. They're theorized to maybe have formed early in the life of the universe. We don't know if they exist. Onwards. Then you have these stellar mass black holes, and they form in supernova explosions. So they're like the corpses of dying stars. They're about like a few times the mass of the sun, and we find many of them in our galaxy, and we assume there are many of them in all the other galaxies as well. So this picture here is an artist's impression of a stellar mass black hole in our galaxy. There should be millions of things like this. And what I work with are these supermassive black holes. They're the big ones. So we have they have a mass of millions to billions of times the sun's mass. We find them in the center of galaxies, and we usually find evidence for like one per galaxy right in the center. There are a couple of cases where you see maybe evidence for two orbiting around each other, which is very exciting, but that seems to be rare. So this is what we're going to be talking about. And to narrow it down even more, I'm interested in what you call an active galactic nucleus, which is a certain state of a supermassive black hole.
Do you want me to do it? No.
So here you see two very pretty spiral galaxies.
So annoying.
And on the right here, what we call a quiescent galaxy. So we think there's black holes in both of these in the center. But you don't see much evidence of it for this one. On the left here you have an active galactic nucleus where you see a lot of light emitted from the very center. And this is light emitted from the immediate surroundings of the supermassive black hole. So that's what we're going to be taking a look at today. And so a kind of basic picture of the life of one of these supermassive black holes is that we have, somehow they're born. And we have a lot of ideas about how they're born, and we're not sure which ones are good ideas yet. So let's just say you get a fairly big black hole at some point early in the life of a galaxy. There are a lot of ideas for this, but 3 question marks. And then they go through quiescent phases and accretion events. And they grow during these accretion events. And how they grow is basically they're fed. So they eat something. As far as we know, they're not sentient, so they don't like actively eat. But matter falls onto them, some of it falls into the black hole, and they grow. And so I'm interested in this accretion, this gas falling onto black holes. How does it work? So if I just have like a clump of gas shaped like a burger here, and I try to throw it, unless my aim is very, very good, I'm gonna miss. And my little clump of gas is gonna orbit this black hole basically forever if it's on its own, because it can't lose its angular momentum, so it just keeps on orbiting. And this is not good if we want to grow black holes to like huge, huge sizes. What is good is these accretion disks, which are ways of feeding black holes very efficiently. They're a way of funneling a lot of gas down near this black hole, and a lot of it falls onto it. And you need an efficient mechanism to grow these black holes, because some of my colleagues here at the University of Arizona, they keep on finding supermassive black holes, pretty big ones, earlier and earlier in the history of the universe. And it gets more and more difficult to explain how they grow so big. So like, it's important to try and understand this accretion process and see whether it actually works and whether it's quick enough to grow very big black holes very quickly. So the accretion disk is basically, if you have some gas in the host galaxy and it has some rotation relative to the black hole, it'll collapse in one direction or the other. It'll form like a disk. And this is a very good way of transporting gas inwards and transporting the angular momentum outwards. And you have fast-moving gas in the middle, slower-moving gas outside, and you get some friction between these different rotation speeds. And so it heats up, it becomes white hot. And that's why we see, when you have gas falling into a black hole, that's why we think it lights up and kind of, you get this very sharp point of light in the middle of the galaxy that can, in the worst cases, outshine the galaxy because there's so much light coming off this process. Okay, so we have like a standard model for how these active galactic nuclei look. This model is not correct, but it's interesting to try and probe the ways it's not correct. And these active galactic nuclei, they emit radiation at like all wavelengths, basically, from like the very high energy X-rays and gamma rays through visible light down to microwaves and radio. And like a good rule of thumb for this model is it predicts that the very high energy stuff, your X-rays, they come from the very central regions. And the low energy, long wavelength things, the radio and microwaves, they come from like far out. And I'm interested in the inner bits today. Yeah. So I think I've got the slides in the wrong order. There we go. So the X-ray region, where the X-ray emission comes from, this is, according to this model, it's like a very compact region in the very central regions of the black hole. About the size of like the distance light can travel in a few minutes. So this is comparable to like the size of like the distance between the Earth and the Sun, which is pretty big on human scales, but like we're talking about something that's like millions or billions of solar masses. It's surprisingly compact. And then we're going to be talking about the accretion disk. This disk I showed you before, and the size scale of that is a few light days, so it's like bigger than our solar system, but on galactic scale still pretty small. We can't see any of these things in an image for accreting black holes. They're too far away and too compact. So we need to use other methods to study them. But the accretion disk, it emits like visible and ultraviolet light. Okay, so I'm going to be talking about variability. So here's a quick example of how we use the variability of the brightness of black holes to tell you something about their size and shape, their geometry. So this is what we call a light curve. This is what we call a light curve. And this is a light curve of the X-ray emission of an active galactic nucleus. So we have, along the x-axis, we have time. And up the y-axis, we have how bright this thing is in X-rays. And you can see it varies quite a lot. In particular, we have this very sharp peak here, which tells you that it doubles in X-ray brightness over like a quarter of an hour That's quite quick. And this tells you something about the maximum size of the region that emits these X-rays. Because the speed of light, it's kind of the speed limit for transferring any kind of information. So if this region was bigger than 15 light minutes, then one side of the X-ray emitting region wouldn't be able to tell the other side that, hey, it's time to brighten, it's time to dim. So this wouldn't happen coherently. So this is one of the main lines of evidence that tells us that this X-ray emitting region is really compact, that it varies very quickly. Okay, so now I'm going to get to this technique called echo mapping or reverberation mapping. And the thing I like about American TV, most of all, is when you have like a courtroom drama and the attorney shouts, "Objection!" So I recorded myself shouting, "Objection!" in 3 different rooms. There's an objection in a small recording studio, a concrete stairwell, and in this giant cathedral in Barcelona. And I want you to kind of try and guess which is which. I'm going to shout it out at the end. So can you play the 3 sound files, one after the other? This is number 1. Objection. Listen carefully. And this is number 2. Objection. And this is number 3.
Hold on. That wasn't really audible.
That was super quiet for
Can
me.
you turn
but
up your speaker? Yeah, try it again. Okay.
All right.
Try it again.
Try it again. Start it from the beginning.
all right, yeah. Objection. Number 2. Objection. And number 3. Objection. Okay, that's more convincing. So shout out all together. We'll see if we harmonize. Which one was the cathedral?
3.
Thank you. Good. Okay, so can we listen to 1 and 2 again? Objection. Number 2. Objection. Which one was the horrible concrete stairwell?
1.
I'm really impressed. You're ready to do like reverberation mapping physics. So what you're doing is like through intuition or through knowing what a cathedral sounds like or some mixture of the two, you're extracting information about the geometry and perhaps also the physics of these rooms just by listening to the echo. I'm impressed you could hear the concrete stairwell because I wasn't sure how that was going to go outside, but like concrete, even though it's a similar size room, it gives you more of a slap back. So you can learn something through listening to these echoes. Objection! Objection! Whoa. Objection! I think I'm just clicking on these now.
Yeah.
Okay, and the obvious twist is that I did not go to Barcelona to record this for this talk. If you want to pay for that next year, I'll do it. But this is like a technique where you capture the acoustics of the room, and then you can use it via some computer trickery to make a sound like it was in a certain room. I'm going to go through how we do this, and this does have a point. So what you do is you make a short, sharp sound in the room. Like, it could be popping a balloon. You call this the impulse. You play this into the room. You record the echoes of this sound. You call it the response. You feed it into a computer, and you get the computer to give you what's called the impulse response function, which tells you how this room responds to a short, sharp sound. And so this is the impulse response of the cathedral we just listened to in Barcelona. And basically you can see, you can go into a lot of detail with this, but the main thing is it's pretty long. And I think you all know like a cathedral's a big room. So some of the echoes coming from the back of the cathedral, they take a long time to get to us. Okay, so like, I'm doing something surprisingly similar, just with light instead of sound. So the accretion disk of an AGN, active galactic nuclei, you can't see it for any of these highly active, highly accreting sources. So you need to use some other tricks. So we make like a model of the accretion disk, where basically you have the black hole at the center, And then, like we talked about, it's hottest towards the middle, towards the black hole. And it's coolest in the outer regions. And because it's hottest towards the middle, most of the blue light from the accretion disk comes from the central region. And most of the red light comes from the outer region, because blue light is higher energy than red light. In the middle here, we have the X-ray emitting region, which is compact, according to our model, and has the highest energy. So this is emitting X-rays. And the trick is that this X-ray emitting region should also shine on the disk. And the disk is pretty thick. It's like a thick disk of gas. So when you kind of pump X-rays into this disk, it'll heat it up. If you pump a lot of X-rays, it'll make it shine a little brighter. If you turn down the X-ray source, it'll cool a little bit, shine a little bit less. So when this X-ray source varies, as it does, you basically get echoes of these variations moving out through the disk. And how long the echoes take basically depend on how long it takes the X-rays to reach the outer part of the disk. From there, the kind of path length to the viewer is the same. And it's especially good if you get like a very short, sharp X-ray flash here, because that's like our popping balloon in the audio example. Okay, so this is very simple in principle. In practice, it's difficult because you have to observe one AGN, preferably twice a day for like months or years. This wasn't really done for the very compact regions until we got this Swift satellite, which is a great tool for this because it can observe with X-rays and in ultraviolet optical at the same time, and it's increasingly flexible because it's kind of completed its main mission, so they're letting us do more with it now. So this has kind of revolutionized the study of accretion disks. This is like the first data set from echo mapping experiments with Swift for accretion disks. It's pretty beautiful. These are light curves for the ultraviolet, so for the hot inner disk, through blue, green, down to the red light in the outer disk. And you see that you basically see the same flares. So it gets brighter here, it gets a bit dimmer here. And to first order, this is like what we expect. We're seeing like a signal propagating outwards as if it was a light echo in the disk. So this is great. This is what people expected for many years. We can finally test it. The problem is that if you look at the X-rays, which is supposed to be the cause of these echoes, it doesn't match up at all for this object. The X-rays don't look anything like, the X-rays at the top here, they don't look anything like the ultraviolet light curve. So for this object, it seems like the X-rays aren't actually causing these echoes. You have to kind of puzzle, okay, what is causing what looks very like an echo signal here? So you saw this for a few AGN, the first few that we did this experiment with, and saw similar results, like the X-rays don't correlate very well with what's happening in the UV and the optical. So it doesn't seem like the X-rays are driving the accretion disk variability. And you kind of have to rethink your model. And one suggestion is to have the inner disk be puffed up so the X-rays don't directly illuminate the outer disk, where we're seeing like the ultraviolet and blue and red emission. So there are a few other reasons, like you might think this happened. It's not just like a kind of quick fix just to solve this one problem, but it does solve this one problem for this object. The thing is, like, as soon as you fix one, another one turns up where it doesn't solve at all. So this is one I've been looking at, an active galactic nucleus I've been looking at for a few years. And in this figure, we've got the light curve again, and the black is the X-rays. And the other colors are all ultraviolet. This is with Swift again. Swift is fantastic. And you just see the X-rays and ultraviolet pretty much vary in exactly the same way. So it looks like, for this object, the X-rays are totally powering this variability. Unless you think too hard about it, because what we have here is a very strong response, a very strong echo, but the delay from the X-rays to the UV, the ultraviolet, is just too long. It's 3 days. And if you remember, like, the X-rays are supposed to be produced very close to the black hole. The ultraviolet, that's supposed to be the inner part of the disk, so also very close to the black hole. 3 days just doesn't work. This should be like hours, according to the standard model. So now we've got to think up a way to fix this. And there are a couple of ideas for this object. So kind of the simplest one is if the X-ray source is just very high above the disk, because then you get a longer echo. And there are some models that do this, but like this AGN is extreme. It's hard to explain how the X-ray source gets all the way up there. How would it be powered when it's so far from the black hole where all the action is? You can also just remove the middle part of the disk, because then you also get like a longer time for the X-ray variability to kind of hit the edge of the disk here, so you get a longer echo. But why? Like, this is very ad hoc. There are some theoretical reasons why you might think this might be happening, especially for this particular object. But we don't really know yet. And the third kind of solution we came up with is maybe the echoes are not echoing off the disk at all, but they're echoing off some of the other junk that's around this active galactic nucleus further out. But then you have the puzzle, like, why would a more distant reflector outshine the accretion disk? So if you think about it, if you have a mirror and you hold a light bulb close to the mirror, it reflects a lot of light. If you hold a light bulb further away from the mirror, it reflects less light. So this is kind of weird. Why would this be? It might be a mixture of all these things. It might be none of them. I do not have an answer for you. I've got a summary. So this technique, echo mapping, it's fantastic. It's teaching us a lot. And the Swift satellite is a really good tool for this. The basic idea of outward propagating echoes works. We see this in the data. Like, first we see variability in the hot part, then in the cool part. In detail, this X-ray lamppost model, where the X-rays are the source of the variability, doesn't work at all. And it fails in different ways for different objects, so it's kind of difficult to fix. So I'd say we're learning a lot through this technique about what we don't understand about accretion disks. And it's still early days. Like, they started doing this with Swift in like 2014, so we got time yet. Okay.
Questions?
Hey.
You said the size of the black hole is determined by weight. How does that correlate the wavelength with the weight of the
Yeah. Yeah. So the question is, correct me if I'm wrong, that the size of the black hole correlates with the weight, the mass of the black hole?
and
Yes.
what does the wavelength have to do with the weight?
Yeah, that's a great question. So the size of the black hole kind of sets the size of the accretion disk, because if you get too close to the black hole, you fall into the black hole. The black hole has an event horizon beyond which everything falls in, and a little bit further out you can't have like a stable disk. So the size of the inner edge of the accretion disk sets its temperature in a way that I think is a bit backwards. If you have a very large accretion disk, it's not very hot, it's quite cool. If you have a small black hole, a small accretion disk, it gets very hot. So the stellar mass black holes, they have accretion disks that reach X-ray temperatures, whereas these supermassive black holes have cooler accretion disks that emit in the UV, in the visible. Does that help?
Why is that? Why is it that the more massive ones are cooler?
So basically, why is it the more massive ones are cooler? It's to do with the steepness of the gravitational potential. So if you have like a very massive black hole, the difference in gravitational force between here and here, as I move toward the event horizon, is quite shallow. For a huge black hole, I can fall into the event horizon without really noticing it. Whereas for a small black hole, it's a lot steeper in terms of like physical length. So I'll just get torn to shreds as I get near it. Yeah.
So when you were talking about like how black holes kind of feed off of whatever they feed off of, essentially, we don't really know. Is that kind of proportional to how big they grow, or how is it where if there's nothing in a galaxy, these black holes grow bigger without having subsequent energy or food to feed them? Or where does that come from?
Yes. Okay, so the question is, how do these black holes grow? Keep on growing? How does this relate to gas in the galaxy? Right?
Essentially, like, I just don't, like, if they're growing bigger, like, what actually feeds them, or is there enough matter or whatever there is to feed them to grow them bigger?
Yeah. Okay, great question. So you need to force some gas from the host galaxy, the black hole's like home galaxy, towards the black hole. And that's a very difficult problem to solve because the black hole, like, it's big, but compared to a galaxy, it's tiny. And it doesn't even dominate the gravity of the center of the galaxy. So you need some way of forcing gas towards the black hole for these accretion events to happen. We think they happen intermittently, either because you have two galaxies colliding, what we call a galaxy merger, which we do see happening like through the history of the universe. Small galaxies collide together, become big galaxies. And like you can simulate this and it should force some gas towards the black hole. So that's one possible explanation. When you try and look at the statistics of AGN activity, so gas falling onto black holes, versus merger activity, so galaxies colliding, there's not that strong a link. We think this is the case only for the most massive black holes, like the brightest AGN, that they're fueled by mergers. Otherwise, there must be some kind of process in the host galaxy that forces gas towards the center. And that's likely, or that might be to do with stellar dynamics, kind of driving gas towards the center. If you have these spiral galaxies, especially if they have like a bar in the center, that's not so symmetric, it could drive some gas. But it's not well understood. The biggest one's probably fueled by mergers.
One more? Okay, I have a question. So you said that you're just getting started on doing this kind of work with Swift, which is really cool and exciting, but we astronomers like to look, 10, 20, 30 years in the future. So my question is, what are you excited about that's the next thing on the horizon for doing this kind of work?
Yeah, so this is a bit of a problem because Swift is middle-aged, let's say. It's done a fantastic job. It completed its first mission, which was to study gamma ray bursts. I think they call it Swift, like analogous to like a little swift bird, because it can turn very quickly and look at things. So it's good at finding gamma ray bursts. It's done a great job there. It's starting to break. It had a stabilizer wheel that failed last year, and people panicked about like maybe Swift's not going to work anymore. And Swift is great for doing this work because it observes with X-rays, UV, optical. There aren't any other satellites that are definitely going up that are so good at like observing in the UV, and that have this kind of simultaneous X-ray, UV, optical feature. So what I'm excited about is that Swift is going to carry on working for the next 10 years. We're getting better at using other telescopes like ground-based as well, but some of it has to be space-based. So.
But you can't do UV and X-ray from the ground. Telling me, I do stuff that benefits from UV, so I'm also sad about that. All right, so let's give our speaker one last round of applause. All right, we are now into intermission. 20 minutes, so it is now 8:05, so I will see you back here at 8:25. Don't forget to grab another beer, tip your bartenders. Don't forget to come and check out our sweet, sweet merch over here. Sorry, it's only cash only, but please come and check it out. And feel free to approach any of us or our speaker with questions afterwards. I'm going to go ahead and volunteer the speaker for that. And we'll see you in 20 minutes.
Yes, I'm an engineer, he's a scientist. So this kind of
I'll try for this next one. Hi.
No, I blame my friend from Phoenix. Every time he's come down in the last 3 months, every time he comes down like to campus, he always brings the bad weather with him. Every time. I was gonna go like, I think the last I'd say the last time there was probably good weather was when we brought the telescope the last time.
I don't know.
Yeah, we'd love to have that.
Knock on wood.
No, I know. And the wind is died down.
Yo, to be fair, drought is drought, but just, like make it happen like.
Yeah.
I just
How does she do that and the sartorial expression?
Oh, you know you're talented, bro. You got this.
Well, thanks.
As a matter of fact, I got a phone call yesterday. I actually had lunch with him and I and we chatted. So I actually got to meet them in
It's like on the verge of
so starting Thursday, I'm gonna pick it up and like give you the like this is the data for like a couple of galaxies and try to
Also,
Yeah, let's try it and then it starts.
starting MC while a train is going. Choo-choo!
Choo-choo!
All right. Welcome back from intermission. I'm going to talk over the train. Welcome back. So we are starting with our brand new Astronomy in the News segment by Jackie Champagne, followed by our second speaker, Afi Khan. And so please give a round of applause for Jackie Champagne.
Woo!
Thank you. Let's get started. Okay.
You need to have your camera on.
It might not be live.
No, sorry.
PowerPoint's not live. Okay. Welcome to Astronomy in the News. If you missed us last month, this is a new segment that we have imported over from Austin, Texas. It was started by the Astronomy on Tap chapter there and was led by myself and Dr. Danny, who is not here tonight because he's on a plane to go see Bruce Springsteen. So that is what he has chosen to do instead of this. I mean, that's fine. I agree. Uh-oh. Oh, no.
No, that's my slide.
Okay.
There we go.
Alrighty. Anyway, the point is that here we give the latest headlines in astronomy and space news with a flair of smiles. Okay, so let's get started. NASA is ripping off Ghostbusters. So I bet you never thought of NASA as being masters of haute couture, but it has been officially decided that NASA will discontinue the giant Marshmallow Man spacesuit of yore. And in keeping with its theme of just cosplaying characters from Ghostbusters, they chose the Ghostbusting suits from the 2016 remake as their inspiration. So an updated sense of fashion will soon be necessary in order to impress our lovely moon, whose surface will soon be tread upon in Neil Armstrong's giant leap footsteps. So, in fact, the moon's American tourism economy has been dead since the Apollo missions, but NASA has a twin mission up its sleeve, because we always have to do like clever little Greek names. So these upcoming missions are called Artemis. And Artemis 1 was an uncrewed mission designed to test NASA's fancy new rocket and Orion spacecraft, which successfully visited the moon and returned in this past December. Artemis 2, in conjunction with the Canadian Space Agency, is on the horizon now, and NASA hopes to appoint 4 astronauts for the crewed follow-up mission sometime in the next year. So this is from a media event at the Johnson Space Center, where they revealed the new spacesuit prototype designed by a company called Axiom Space. It features a few updated features, including an improved range of motion over the old Marshmallow suit, so more science can be done on the lunar surface. Most importantly, it is more easily altered for sizing than the old Apollo mission suit, because in classic American history fashion, all 12 NASA astronauts that have been to the moon were white dudes of similar build. So they only made one kind of spacesuit, and it turns out that doesn't fit most people. But at long last, the new suit is designed to fit astronauts of any gender and height, and NASA promises to announce both the first female astronaut and the first astronaut of color to touch the lunar surface. The final Artemis mission is planned to visit the lunar South Pole, which is uncharted territory of the lunar manifest destiny. The devil might wear Prada, but the angels of the Artemis 3 mission will be clad in all white. White suits for summer. Groundbreaking for sure. However, there is good reason, and that is because the harsh sunlight and extremely hot temperatures of the lunar South Pole demand a highly reflective suit. So we can expect some more slimmed down marshmallows in the final prototype of what they're calling the Axiom Extravehicular Mobility Unit, or spacesuit. Bear with me. The Tucson humidity is making it very difficult to move my papers around. Okay. A dram of Titan. So Danny and I both share a love of Titan, which is the largest and iciest moon of Saturn and the second largest moon in the solar system. It's actually bigger than Mercury. Titan is extremely cool because it contains an atmosphere and a subsurface ocean that is made of liquid water and atmospheric pressure about 50% of Earth's. So possibly the coolest fact about Titan is that its surface temperature of minus 290 degrees Fahrenheit places it at the triple point of methane, meaning that you can have methane clouds, rain, oceans, and ice, all on the same little body, which could create ideal conditions for methanogenic life to exist. But much cooler, however, is because of all the methane in this environment and the low atmospheric pressure means that A, you can fly on Titan, but B, you probably don't want to because it smells like farts. But anyway, NASA announced in 2019 a new mission called Dragonfly, which will be a drone-like rover that is going to visit Titan's surface. It will be the first of NASA's missions to land a robotic multi-rotor vehicle on another planet, whose full science payload will have targeted access to surface materials. If you're thinking, of course we sent rovers to Mars, I think that too, and I don't really know what the difference is, but it said multi-rotor. So it is set to launch in 2027, but it will take approximately 8 years to reach Titan. So it's going to take some time, but then we will get some really cool scientific results. So NASA is in the process of revealing the instruments that will be aboard the Dragonfly, one of which is being developed at the Johns Hopkins Applied Physics Laboratory, and it's called the Dragonfly, I'll be all right, the Dragonfly Mass Spectrometer, or DRAMS. It will take a little bit of Titan's moon and less than a gram per sample of Titan's surface material delivered by the drill for acquisition of complex organics. But we don't want Draco to malfunction because DRAMS will shoot lasers at Titan's soil to learn about its chemical composition. So basically this instrument is going to separate the components of the sample into its base molecules and pass it through sensors which determine the weight, charge, and identity of various molecules present. So this is a mass spectrometer. In astronomy we're used to working with light because of course we can't go visit black holes and other galaxies, but it's really cool that the planetary scientists can do mass spectrometing. Anyways, scientists hope to uncover organic or carbon-based molecules, which are the basic building blocks of all known forms of life. So scientists have hypothesized the composition of Titan's surface. This will mark the first time that we've ever actually taken a tiny taste of another moon and investigate how pre-life chemistry can evolve in other worlds and potentially create fart aliens. And finally, we have myriad signatures of complex molecules in new stars. This is from the James Webb Space Telescope, the MIRI mid-infrared instrument. So basically, in order for any result to make it into space news in general, you either have to claim that you found the first galaxy that was ever formed in the entire universe, or you have to claim that you found aliens. And they find new and exciting ways to claim this. And so too was this article. It's about stars, but they were like, could be aliens. So the article claims that complex molecules that are necessary for life to arise have been discovered in a young star. So let's just hold our horses and just talk about some chemistry. So this is, like I said, from the James Webb Space Telescope, from yet another tortured acronym. This is going to be a theme of all of the space news that I deliver to you, is that astronomers really love to just make up words and then come up with letters. And they have nothing to do with anything else. So are you ready for this one? This is called carinos, the complex organic molecule, one word, origin, investigated by the Next Generation Observatory, one word, in space. Carinos, not to be confused with Doritos or any other sensible acronym. So anyway, carinos reports a mid-infrared study of a protostar. So you can think of this as a newborn star that's basically still connected to its cosmic placenta. This is an envelope of infalling matter, which has spawned the star itself, but there's still this like cloud of stuff that's all around it, and it hosts a number of complex chemical reactions, and basically many of these are going to occur on the surfaces of grains of ice, but eventually this is going to migrate into the warmer gas. So as these molecules absorb mid-infrared frequencies of light, a bunch of crazy stuff happens. The molecule can stretch or bend or vibrate. So that's going to produce a characteristic signature if you were to observe it with a mid-infrared spectrograph. So basically like shining it through a prism, you know, you get your rainbow of light. This is a little bit more sophisticated. And so you can't really see the labels here, but I will explain some fun stuff to you. So prior to the launch of JWST, we did not have fine enough spectral resolution to examine the individual features with this kind of crystal clear detail. You might have just gotten, you know, a vague curve, but you're not really sure which molecules are which. So like I said in the previous slide, with mass, what's the spectrometry? Spectrometry, that's the word. With that, you get an actual sample, right? And you break it up, and when you shoot lasers at it, it tells you exactly what it's made of. You can do the same thing with light, and you need to do it with light for these very complex molecules because, well, that's all that's accessible to us, really. But you know, very simple molecules and atoms, things like hydrogen, very simple, very easy little signatures, and those are the kinds of things that I like to deal with. The more complex your molecule gets, the harder it is to disentangle what all these signatures are. So I have to refer to my notes to even know what they are. So this is coming from the Astrophysical Journal. This is a research scientist at the Japanese Reiken Institute led by Yaolin Yang. He was a grad student at UT Austin with me, so it's very exciting to see him in this press release. We are seeing the incredible spectrum of a protostar envelope with its detailed chemical composition. So this is confirming the presence of water ice, carbon dioxide, silicate dust, ammonia, methane, methanol, formaldehyde, and a couple of other ones that I couldn't even pronounce, let alone spell, but you can imagine them. They're all organic molecules. So the image that's pictured at the left here is you can see these kind of like shell structures here, and this is being produced by an outflow or a jet of hot gas that is traveling.
Choo-choo!
This is traveling hundreds of kilometers per second, and so the nerve. So I don't know if you can tell from the contrast in this slide, but there are 4 kind of shells to this, and this is giving you an idea that the longest train I've ever seen. Okay, anyway, there are these shell-like structures, and that's basically telling you that there's an episodic nature to this outflow. It's not just spitting out stuff all the time. There is something that is causing, you know, accelerations and collisions in there. In addition to the spectrum of the protostar itself, from this outflow, they have also detected signatures of hydrogen, iron, nickel, neon, argon, and sulfur. So if there are any young people in the audience that are maybe interested in pursuing a science career, and the one thing that you're really good at is memorizing the periodic table of the elements, you might want to become a stellar scientist because it's a very exciting new era for James Webb and all the people that study stars. Which is not me. So that's why I'm completely at sea with this, but I hope that you learned something. I'm going to stop there so we can get to our next speaker, but if anyone is super interested in learning about galaxies at super high redshift, I do have a bonus story that I'm happy to share with you all at the end. So thank you very much for listening, and I'll see you guys next month.
All right. And with that, let's welcome our final speaker. My friend and colleague, Afi Khan, is going to bring his little friend and tell us about flying space balloon. Come on, buddy. Come on. It's shy, I guess. Come on, buddy. Yay! He did it! Okay. I need to give you the things.
All right, Neetu, the stage is all yours. All right, so space balloons. haven't we been in the news lately? But I'm not going to talk about the balloons that look down at your houses trying to figure out if you're like trying to take... Oh, sorry. Can you hear me now?
Yeah.
Space balloons. We have been in the news lately because President Biden has been shooting us down. We're not the kind that Biden would like to shoot down, though. We don't look down at people. We look. So yes. Can anyone guess, with specifically people who did not get a sneak peek preview of my slides earlier, how many galaxies are there in this universe? Any guesses? How many galaxies in the entire universe? 5? Infinite.
More than 3.
Yeah, cheater. Cheater. Yeah, so 200 billion is a good number because that's what you saw on my slide. Right? You know, when somebody comes up with a round figure answer in their scientific results or lab notebooks, I'm like, yeah, you really did not get that round. But, well, we don't know, but 200 billion is a good guess. Some astronomers think it could be up to 1 trillion galaxies. Just put your mind to it. 1 trillion galaxies. Each galaxy is with 100 billion to 1 trillion stars. I'm not going to count the number of zeros and how many stars and how many planets there can be. I'm interested in how all these galaxies form, how they evolve over time, and actually just a question, why are there galaxies in the universe? When we look around, we not only see these galaxies, but we see that they're not just isolated islands of stars, but they are sort of connected to each other in this vast network of gas and something called dark matter that I don't have any idea what it is, and somebody can explain it to you offline. I believe in dark matter. It exists, but I don't know what it is, and so does none of the smart-ass astronomers that I've been in this audience, so please. Anyway, but we know what we know about dark matter is that it is the background to which all the galaxies exist in, where the concentration of dark matter is large. We call these regions the halos, and a galaxy which is made up of ordinary material that makes you, your car, your stars, and your dog. No, my dog is made up of special materials. You're special, Neetu. Anyway, but not dark matter. He's made up of white matter. And so enough with the jokes. I have to cut down on the jokes. This is not a stand-up performance. For that, you can come on Friday. I'll be doing the stand-up. But anyway, so there is this large network of galaxies which is connected by gas. The gas, I say, is just ordinary dust, and dark matter sort of plays a role in this. I'll talk a little bit more about cosmic web, and that's why it's called the cosmic web. Yeah, astronomers are not really smart at making up acronyms or names, so they just like very literal, not really creative. So the cosmic wave is basically the large-scale structure of the universe. It's filled with mostly dark matter, but there is sparing amount of gas, and we are made out of some small amount of that material. And to just give you an idea of how it looks like, on the left-hand side you have, right-hand side. On the right-hand side you have like a cube of the universe simulated in a computer of how everything kind of looks like. On this side you basically have a slice of it. If you kind of slice through it and look through this cube and see what it is, and it kind of looks like a web. Guys in the audience who are not astronomers, because astronomers think it looks like a web. What about the non-astronomers in the audience?
Vascular system.
Yeah, vascular system, network of neurons. So there were so many other things we could have called it, but we were like, web, because we all like spiders. I don't know why. so this web. So what this technically shows you is distribution of dark matter and how there is like small concentration of dark matter through the universe, and the gas kind of follows this dark matter because it's the dominant content in the universe, and it has what is called as gravity. So it pulls on all the ordinary material and gas towards it, and that's where the galaxies form. So if you look at this simulation, on the right hand side we again have dark matter distribution, and on the left hand side we have distribution of the gas kind of being represented by its temperature. And this simulation is running through cosmic time. So in the beginning everything was sort of very, very hot, but then it cooled down and everything was really dark before stars formed. But then the gas started to sort of fall into these regions where the dark matter is heavy, and you see all the galaxies forming along these intricate highways of dark matter. So we have galaxies because dark matter has a structure, and the galaxies sort of form in this structure. But, well, if you turn the clock back and go long time ago, even before there was any far away galaxy, the entire universe was filled with hot gas. It was extremely uniform. I mean, the variation in the temperature of this gas and density of this gas was like 1 part per million. So if something's slightly warm here, then the neighbor is like 1 million times cooler. And if something's slightly dense in one part of the sky, the other part is like 1 million times less denser. So how do you come from this like really uniform universe to all these galaxies and stars and the structure of the universe? We sort of know the answer, but we have also wild guesses of how things go. And we make these wild guesses by looking at the universe and trying to understand it. And the wild guesses are based on some mathematics, and that's the field of astronomy for you. We make a lot of wild guesses. Most of them turn out to be right. So if you have somebody who's trying to pursue astronomy, it's a great field. But how do all these galaxies form? This image is taken from the James Webb Space Telescope, and it's like a tiny piece of sky. It's like they give this analogy at all the talks where you like take the tip of the ballpoint pen, point it at the sky, and the size of the sky that you pick out from that tiny patch, all these galaxies are in that tiny patch, and there are like hundreds and thousands of them, and that's why they have like an estimate that there are 200 billion galaxies. And it's a very pretty picture, so it was on the cover of the Time magazine, but so were some very nasty politicians. It's not a great thing. I think it's not doing justice. Can you play this video? I'm sorry, it should have been an autoplay, but yeah, just play the button. So, start playing. Oh my god, it was a great video. Anyway, is it seriously not playing? I'll skip through this, no problem. So, what that video was trying to show you was how, out of that entire structure, a single galaxy has appeared. So, the earlier simulation that you saw, the largest scale of the universe, kind of zooming into one galaxy. And what happens over cosmic time is that the gas and material which is formed during the Big Bang, which was very uniformly distributed, eventually clumps into these halos of dark matter, spirals around, swirls around, and becomes cool enough to form stars. And that collection of stars is what we call a galaxy. And when you are trying to understand how these galaxies actually form by tracking all this material in the universe through some of these fascinating simulations that I don't do, some of my colleagues do that, we end up understanding that these galaxies basically are like recycling machines, or some people call it the galactic fountain. So this is a representation of a galaxy. So all the stars and the dust that you kind of have seen on this pretty picture, all that is this small central part of the galaxy. So my colleague before this was talking about the big black hole at the center of the galaxy. That's 1 pixel in this image. So this is a much larger zoomed out version of a galaxy, and the galaxy is only tiny. I show this because what I care about is not even the galaxy, but the gas around it in my research. And why, you would ask, why do you worry about this tenuous gas? And the reason why I worry about this tenuous gas is because when we look at all the simulations like the one I played for you and the observations that support those simulations, we believe that this tenuous gas around galaxies plays an important role in how they evolve, whether they will form stars, the star formation inside those galaxies, how they kind of impact the material that surrounds galaxies and other galaxies that might form around these galaxies. So what happens is that inside the galaxy, this gas is falling, This infalling gas might cool, form stars. These form stars might eject some material. Sometimes what the stars do is that inside their core they take lighter material, fuse it into heavier material, but in the end of their life they just explode like supernovae. Actually, they are called supernovae. The word supernova comes from that. And these supernovae then spill this heavier material out into the universe or out into the galaxy for new stars to form. So we are actually all made up of exploding stars. It's not a joke. It's serious. And so these exploding stars also enrich the surrounding gas of the galaxy. And by understanding the surrounding gas, we can then see how the composition of galaxies varies over time, how the stars within the galaxy and their composition varies over time, and it kind of tells us very interesting things about galactic evolution. So it's like a small piece of puzzle that we're trying to put together in our understanding of the universe. One missing piece, a big missing piece, is that when we look at all the baryons, all the material that make you, me, and my dog, not my dog, you, me, and everybody else, my wife will be watching this video, so I have to be really nice about my dog. I really love it. And so the ordinary material that makes us, which is not dark matter, we kind of cannot account for almost 30% of it. And there are many theories of where this material lies. Some people have a consensus that, well, this material is actually around the galaxy. It's not inside the galaxy, because you take all the star dust, all the planets inside a galaxy, and you do all the math and you compare it to how much material was there at the beginning of the universe, because we can see all of it. We find that, well, 30% is missing, and that's a big accounting error. That can sink a lot of big bangs. Not that it's happening. I'm sorry if you're affected by this tragedy, but if 30% of the material in the universe is missing, you might be like, hey, astronomers, do your job. You take all these multi-million-dollar fundings and you don't know 30% of the material where it is. So I'm trying to be that astronomer who kind of tracks this 30% material. We believe that it's in this tenuous gas, which is being recycled into the galaxy, so forming new stars, which is enriching the diffuse gas that is in the larger cosmic web, and that also is getting gas content from this larger cosmic web into galaxies and finally eventually into the center of all the stars that are being formed. So this is the question that I'm trying to understand, how this galactic fountain kind of works over time, and it's very hard to do this because this gas around the galaxies is extremely diffuse. When you look at a galaxy, you only see the galaxies, you see the stars, they're really bright. When you try to look for this diffuse gas, they say, no, sorry, thank you, come again with a bigger telescope. And so I'm trying to the answer is not bigger telescope, but smaller or better telescopes. But the big picture is, let me summarize it amidst all the jokes, that the gas from the cosmic web gets accreted into the galaxy, eventually cools down, can form these stars, can lead to star formation. These stars explode into supernovae. That material from the supernovae can remain within the galaxy and form other stars and planets. But sometimes these explosions are so energetic that the gas kind of is thrown out. Then, as we heard in the previous talk, there are these large black holes and with their accretion disk in the center of the galaxy. Sometimes these black holes become so active, they're called the active galactic nuclei. Again, we are so good at naming things. The active galactic nuclei can be so energetic that they can spew out the surrounding gas into this tenuous atmosphere of gas around the galaxies. By the way, it's called the circumgalactic medium. And what this circumgalactic medium is very diffuse gas, so like 1 atom per square mile, probably even less diffuse. I'm just trying to give a simple example. So 1 atom of gas in a very large space of volume. So if you have to detect this, you have to look at light either emitted from this gas or light that has been absorbed by this gas. So that's where comes a quick session in two quick lessons in spectroscopy, because you heard that word a lot. If there's a bright star, it has some emission, and if you look at that light and you split it with a prism, you would see a spectrum of light, which I like to call just the rainbow. And this rainbow has all the wavelengths of light. But sometimes this light from a star can pass through a gas cloud, and two things can happen to it. Well, some of it can be absorbed, some of it can be scattered. So if you're on the other side over here, you'll not see the full spectrum. You will see some features that are absorbing. And I'll talk about what is this absorption, but it's basically a signature of the content of this gas. We will come to that in our next lecture. You will have to pay $5,000 tuition for that. But in this lecture, we just talk about what happens to that gas and what happens to the light that's coming through, passing through the cloud. Sometimes this cloud can be hot, like the gas that we were talking about, the circumgalactic matter, and that can emit light on its own. And that light looks completely opposite, but sometimes just like a mirror image of wherever there was light, you only see these lines because that's the emission spectrum from this gas. And it's all happening due to atomic mechanics, which is way beyond the purview of this course. So again, I'm not going to go into the details, but basically the atomic transitions in the atom are responsible for both the emission and in the absorption. Basically an electron gets bumped by the light, gets excited, goes into a higher shell. When it comes back, it starts emitting. So you can get signature of different elements and you can kind of recognize what they are. And if you know what they are, you can make a guess about where they come from. So if you see a galaxy whose surrounding is filled with a lot of metals, early universe did not have a lot of metals, so you can kind of make a guess that, okay, this galaxy has at some point enriched its surrounding with all these metals. And this is kind of a much more detailed picture. I will not go into the details, but you can look at the spectra of these metals and try and predict what material is there. Some of the higher, like heavier metals like oxygen and nitrogen and silicon, they can get excited and they can emit only when they are very, very hot. And luckily the circumgalactic medium is really, really hot. So we see this emission from the circumgalactic medium. If we have a really very good telescope and we are very patient to collect one photon at a time over 5 days, we will be able to make a picture of the circumgalactic medium, and we would be able to see over this how this gas is going around this galaxy over cosmic time. So this is basically cosmic time, and this is basically different properties of these galaxies. But there's one problem. All of this emission is happening in ultraviolet. And unfortunately, bad news, the ultraviolet light from this gas never reaches the Earth. It kind of gets trapped by Earth's atmosphere, which has this ozone layer that protects Earth from the solar radiation to reach us. And as an ultraviolet astronomer, I'm like, what is the point? Give me cancer, but give me some data. Why do I have to build these space telescopes and flying balloons? But anyway, so the ultraviolet radiation allows this visible light to reach all the way here. So you have all these optical astronomers who just have to go on top of the mountain and like look at galaxies and make these pretty pictures. People like me have to build a big space balloon that has to go up into the stratosphere, be worried about shot down by Russian jets or American jets or other countries' jets. Peace. So
hurry up, the train's coming.
Oh yeah, the train is coming. So I'll hurry up and I'll move forward. So because it's all ultraviolet and we can't see it from ground, we have to go up in space, and that's why we make these space balloons and satellites. My choo-choo! Fireball is one of... We all know we all know you're a train. You don't have to announce it so loudly. So anyway, Fireball is a stratospheric balloon. It has a big ultraviolet telescope on it. Goes into, well, why am I explaining this? Let me show it to you. That's a balloon with a lot of helium filled in it. The telescope is somewhere down the line, you'll see it. And, well, what happens is when you're, oops, can we go back? I messed it up. When you're sitting on the top of the telescope, this is what you see. It's slowly rising up. This is New Mexico desert where we launched these balloons from. And you slowly go up all the way. Into the stratosphere, and this is just pretty pictures. What really happens is our telescope opens its doors and starts looking at these galaxies as targets, not trying to really look at the galaxies themselves, but trying to detect the light that is coming down in ultraviolet from the tenuous gas around the galaxies. And so you're already in the stratosphere in this picture, and I'll stop this plug over here. Can I go back one more slide?
Yeah.
Yes.
Do the other.
So I wanted to really show this, because it's pretty cool. Look, could you play it from the console? You can move it forward a little bit, because we already saw that balloon thing go up. Yeah. What is on the other end of the balloon is a big gondola, the size of an SUV. And we have a telescope which has a mirror which is 1 meter wide. A 1 meter wide telescope, and a rainbow making machine called a spectrograph. I don't want to go into the detail. I'm an expert at it, so I can bore you to death about it. But it's a rainbow making machine. It basically takes the light and splits it into different wavelength components. We look at these wavelength components, and just like the signature of sodium and oxygen that you saw in the previous slide, we look for those signature emission lines. And based on how strong these emission lines are, how redshifted they are, because you are looking at galaxies that are far, far away, we can predict about what is the total composition of that galaxy. And you can see that gondola over there. This is a human being for scale. And the person who's talking in French is Bruno Millard, who was one of my advisors from France, but he's retired now. But then this gondola rises up, goes into the stratosphere. You might want to pause the
Il va attendre que ça passe au-dessus.
So the gondola. So the gondola goes up. I'm going to talk over this. The gondola goes up. At some point, we reach a place where we are above the ozone layer. We open the doors and we stare at these galaxies, trying to collect like 10 photons at a time coming to us. And then when it comes down, we analyze the results, trying to look for signature of highly ionized oxygen, highly ionized carbon, trying to map the distribution of this gas around galaxies, and trying to understand like the answer to this big question of why do we have galaxies, where do they come from, and how their evolution connects to formation of stars inside galaxies, and eventually the question of our being. So Fireball went up in 2018. Unfortunately, there was a hole in the balloon and it could not reach its altitude, came down crashing. We couldn't have enough data. We couldn't even collect 10 photons, and we came down crashing. We tried to fly again in 2020. We all know what happened in 2020, 2021, 2022. We failed to launch in 2022 because of a shipping issue. It was not FedEx. We had a shipping issue last year. We couldn't fly. It was not FedEx's fault. They paid me to say this. But we fixed the issues. We are hoping to fly this September, and we will get those 20 photons, and we'll tell you about how the galaxies were formed. But we'll not tell you what dark matter is, because, well, all the best with that. And then the other project that I'm involved with is Aspera. It's a small satellite. It has tiny mirrors, but it goes above the atmosphere, kind of tries to understand the same emission from tenuous gas around the galaxies, in trying to map and understand how galaxies form and evolve over time. And that is all. Thank you. Do you have a question? Like, where's my treat? Any questions? Yes.
Bobby, when this balloon, when everything is right with the world and the balloon goes up, one, how high does this balloon go? And two, what is the lifespan of this balloon, barring nobody shoots it down?
So I will repeat the question. The two questions: how high does this balloon go when you release it, and how long does it stay? So the answer to that question is the problem of my life and why we can only launch it once in a year. So there is a time in the New Mexico desert when the trade winds changed direction, And at that point, the winds are not fast enough to take this balloon over to some other country's territory where they'll send jets to shoot it down. Not that that has happened ever, but also the other threat is that this balloon could go over this state called California and fall onto people's houses. And this $20 million telescope could lead to a $20 million lawsuit. So we fly for one night mostly. We have 1 to 5 nights to be in the stratosphere because the winds are not too strong, and it comes back in the New Mexico desert. So that's the time we have to do our science. Does that answer your question?
How
so it's
high?
like a one shot a year, only 5 days, and then you have to wait for another few years. But then the downside is that if you want to send something like this to all the way to orbit, it's probably billions of dollars. So it is interesting science.
So when you showed the video taken from the balloon, it looked pretty jumpy. I'm just curious how you stabilized the telescope enough to be able to point it at one galaxy for 5 days.
That's a great question. So as I said, this is a very sophisticated space, almost like a space telescope. We have what is called as Geiger cam, and the Geiger cam looks at stars, and it looks at the stars in the visible, although the whole telescope is designed to operate in the ultraviolet. The Geiger cam can look at the stars in the visible, and that tells you where the telescope has to point, and we have mechanisms on board the telescope that stabilize both the telescope and also the spectrograph. So the whole instrument which is under the telescope, which kind of is a rainbow making machine, is constantly being tipped, tilted, and rotated very fast to be able to compensate for all the movement of the balloon and the spectrograph and all the dance, and it kind of dances with the wind and takes the data. Does that answer your question?
Yeah, thanks.
So it's very sophisticated engineering, but I didn't want to bore you. This telescope is 1 meter in diameter, and it has a focal length of 200 meter, and it can do a spectral, I'm sorry, just giving an example of how boring it can be. You can come to the colloquia talks I give, you will know how. Anyway, yes?
I think your wife married you for your sense of humor, so go for it. I think
She was like, she's not here, that's why I'm making all these jokes.
No, but she loved you and she loved your dog. So.
Please go ahead, sir.
How long or when is this fair going to be launched?
Brilliant. So today in the lab, I do a lot of the hardware stuff I don't do the simulations, and somebody else does it. I just like to use them because they're pretty. The pictures of my mirrors are like, all right, they look fancy, but the simulations are really pretty. So I build the instruments. I am working on the hardware hands-on. So today morning I was testing some of the test optics for Aspera. We will get the flight optics again. Although they are tiny, they're still sophisticated. It takes almost 5 years to build something like Aspera. We got funded in 2019-ish, 2020-ish, and we plan to launch later in 2025. And because it's a small satellite, it actually relies on rideshare. So it will be sitting next to some big communication satellite or some spy satellite that wants to look down into your houses. And next to it will be this tiny satellite that wants to look at the galaxies. We will launch in 2025. We have an 8-month mission, and we are not looking at all the 200 billion galaxies as much as I want to. We'll only be looking at a few specimens that have been scientifically selected as a decent specimen of certain kind of science that we want to do. And we will be observing those 8 to 10 galaxies with the small sat, so that we can prove that we can make a bigger telescope like the Hubble or the JWST to do this at a much larger scale and prove this. Building UV instruments is very hard because everything absorbs the UV light, your skin, your optics, your mirror coatings, your detectors. So one part of my research is to build detectors that can detect UV better without like completely absorbing it for yourself and give you some information. So all that culmination of technology takes years and years. And Aspera is, for example, a result of 20 years of technology development. And we'll be looking at these nice galaxies, hopefully in 2 years' time. And that's when I plan to graduate. Because of my sense of humor, I told my advisor that the day Aspera is launching, I will defend my thesis at the countdown. Of course, that's not going to happen, but I can be optimistic. Any other questions? One more question at the back.
How does
did they recover the telescope from the balloon?
Ah.
How do you recover it?
So we asked the Air Force to go up and shoot it, and then a flying saucer comes in and kidding. No, I think I'm lying. Yeah. So what happens is that if you, I'm sure that video was we had a little snack with that video, but what I wanted to show was that big line that you attach the gondola to the balloon. Part of that line was just I can't even do shoot with the bus, but part of the line had a parachute attached to it, and so once the balloon we're done with the mission, we cut off the balloon with a pyrotechnic because it's a helium balloon, so it kind of goes away and eventually deflates and falls somewhere, making microplastic pollution in the Pacific. Sorry, I have a little bit of conscience, but that's the reality of things. So the rest of the telescope with the parachute comes down and lands in somebody's farm. We pay them some money to recover our telescope. We don't tell them that it's $20 million, we just say it's a piece of junk. Or we tell them there are aliens inside it, they're going to eat you, and they're like, take it away for free. That's what happened in Roswell. I was there. So they recovered me from the balloon. So what happens is that it lands, and then we recover it. In 2018 flight, because it was all a beep show, we basically not only had a hole in the balloon, but the balloon fell down, the parachute deployed. It was supposed to gently land in the field like plonk, but it did a pshoom. And then not only did it do a pshoom, it also fell on its side. And then the consequence of it was that I spent two months in France, 6 months in New York, and 4 months here just trying to align those optics that have been misaligned. And but we got it done, and University of Arizona knows how to fix telescopes. We fixed Hubble once, if you don't know that. And so we fixed this balloon telescope, and hopefully it will fly in September, fingers crossed. All of you pray for it. Whatever God you believe in, or whatever God you don't believe in, or the flying spaghetti monster you believe in, pray to them that this balloon flies and gets some science rating. Because I don't want to talk about another failed mission next time. I want to talk about the data from the balloon. Thank you so much.
No, your dog's coming home with me. I'm sorry, I don't make the rules. We decided he's gonna. Oh, buddy. All right, well, that's a wrap for SpaceDrafts 85. Please stay tuned for next month. We will be right back here, same time on April 18th. Follow us on Facebook, follow us on Twitter. You can sign up for our mailing list. If you go to astronomyontap.org, go to the Tucson location, you'll find all the links for all of those things, so that you can stay in touch and stay informed with what we are doing. And I hope to see all of you here next month, which is April, on April 18th. And don't forget to tip your bartenders, and don't forget to check out the merch table, still open, and have an excellent evening.